What are we talking about? We're starting to learn techniques for finding closed form versions of open form net accumulation functions, right? All semester we've been writing open form net accumulation functions and then working with GC to graph those and get function values out of those. But then we said, hey, look, there's a big advantage to having closed form. If we can rapid fire spit out values of accumulation really fast. So we're going to go through lots of these techniques of giving for instance, given an open form net accumulation function, find the equivalent closed form. And remember what we said, if there's nothing here, if there's no a and x or values, then we call that an indefinite integral. And what does that really represent? So what do we imagine is there? A and x, and if x, then we're thinking these are t's or some other value. But if it's an indefinite integral, then we're really talking about all possible net accumulation functions that have that rate, right? That are accumulating at that rate. So that means it could be any value of a, and we consider all values of a. All right, and then we saw that at the end, the minus f of a, that's what plus c is, right? That's what the plus c is. It's the minus f of a, because we know this is some f of x minus f of a. That's what this means. And so then we could start at any value a, and then we get a whole family of net accumulation functions, right? All having the same rate of change. Okay, so we did the first technique, which was seeing if we could recognize that our rate function was like the result of a chain rule derivative. We're going to undo that, and you've got lots of practice. You've already started, and that's due Wednesday at 9 a.m. And the goal there is not to just keep repeating the technique I showed you, but eventually you start looking at those and seeing it as a result of a chain rule, and then doing it quickly, right? Doing it very quickly. So those who've learned a substitution technique, if you can keep practicing what I showed you, you can do it 3 times, 4 times as fast as working through all that substitution technique. So that's what I'm hoping that you'll acquire that ability. Okay? So let's do the next. And so that, actually, this undoing the chain rule is kind of like the most important and the most prevalent technique that you'll have. Okay? So, and it becomes part of all the techniques we do next. So we always the first question we'll ask is this a chain rule? Is this undoing the chain rule? That's what we're always going to ask that question first. Okay? Because those are the ones we'll see the most. And you could argue it's kind of the most important technique because they show up the most, and then it's involved in the other techniques. So the next one is undoing the product rule. Undoing the product rule. So what's that? So let's review what the product rule is. The product rule says if you have the product of 2 functions and you want to take the derivative, it's not the derivative of the first times the derivative of the second, right? It's been tried many times throughout the calculus ages by students, and they got it wrong every time. All right? So what is it? It's the first times the derivative of the second plus the second times the derivative of the first. So this one's a little bit different because we're not going to be given a rate function that looks as perfectly like this. So I'll hold that thought for a second. So if the product rule is true, and then we do antiderivative, that means that the original product is the antiderivative of fg prime plus antiderivative of g f prime. Okay? That should make sense, right? Okay, so like I was saying, these problems are not going to be that you're given a rate function that looks like this. It's kind of way too rigged, way too contrived, okay? If you did happen to get a rate function like that and you recognized it, and then you could just write, the antiderivative was fg, that's rarely going to happen, okay? But what actually happens is this. We're given the one that the net accumulation function that we have is like one of those. Okay? It's like, say, this is the given integral. It's of this form. But this is kind of unattainable by whatever our known techniques are. Okay? So then what happens is, and then this one is something that we can do, or is at least easier. Okay? So if that's the case, if we're trying to solve for this one, shaded red, and we know how to get the one shaded green, then what could we do? How could we get this? I know what this is. I could figure out what this is. So then how could I get that? This goes back to your first course in algebra. Yeah?
You could take the integral of g to
Yeah.
f times.
Right. So yeah. So if we can do this, and we can figure out what f and g are, then all we have to do is take fg minus this. You see that? Just subtract the green one from both sides. And so it's kind of like an indirect method, right? So it's kind of like we're not really finding the antiderivative of this directly, but we're kind of doing it indirectly by figuring out what f and g are and figuring out this antiderivative. And then we subtract. We're going to do fg minus that. So here's the strategy. We're going to think of fg prime as one of the terms of the product rule, and we're going to figure out what f and g are. We're going to compute fg, and we're going to find this one, and then we're going to solve by subtracting. Fg minus that is going to be the one we want. So the thing that comes up is then, like, if we have the product of two things, which one is the f and which is the g prime? So that's we'll see that in examples. Okay, any questions about kind of the general idea here? All right, so again, this is what I wrote on the last slide. I'll just put it up at the top. So here we go. Let's try an example. Okay, so the first question we're always going to ask is this the result of a chain rule derivative? Can we use this technique, undoing the chain rule, to do this? I have one no. I have another no. Okay, so what one small change could you make to this? This is just a side question, right? We're gonna do this one, right? We're gonna find the antiderivative of this, or yeah, find the closed form for this net accumulation function, or family of. But as a side question, how could this be slightly different so that undoing the chain rule would apply? And this is a really good question to ask every time so that we practice recognizing undoing the chain rule. So I want everyone to think about it. Just take a couple seconds to think about it and see if you can come up with it. I have my lists. And then if you want to, after thinking about it, if you want to compare your answer. So like kind of what's the smallest change we can make so that it would be undoing the chain rule? Think and then talk. All right, where's Kevin? Salas, Perez, Kevin. Kevin here? Yeah. Did you come up with something?
No.
All right.
That's true.
What one small change could if we made a small change to this, that it would be undoing the chain rule? Where's Jason Alexander? I think I tried him last time. Did he drop? Okay, let's see. How about Kirko? Anthony? Kirko? Okay, we could do that, but then it would just be like sine. So I want to have an actual undoing the chain rule. Is there something else we could do so it's actually undoing the chain rule? And remember, what do we need? We need a composite function. Let's review it. This is super important that we can see these and maybe change them. So This is what we're looking for. And so what's the qualification for undoing the chain rule? There's a composite function, and the other factor is essentially, or a constant multiple of, the derivative of the inside of our composite function. Yes, sir? He wants to square the x inside the cosine. What do you think? So what if it were this? Now would it be undoing the chain rule? Yes, absolutely. We need to see that. So those who are saying no, what is the hesitancy? The 4? Remember, any constant multiple. I could put 4 pi to the e here. We can handle any constant multiple with antiderivatives and derivatives. So what's important is that we have the right powers matching up, right? Derivative of x squared is what to the what power? First power, right? Derivative of x squared is to the first power. So I can have any constant multiple as long as it's x to the first. It's undoing the chain rule. Does everybody see that? Yeah, so we're going to practice that. We're going to keep practicing. If this were 4x cosine of x squared, absolutely undoing the chain rule, okay? But it's not. And I'm out of undos. All right, so we're going to do this. So, for x cosine x. So, maybe it's undoing the product rule. This is my first example on this topic. So, what would we do? We need to figure out what's g and what's f prime. So we're going to have like f, g prime. To figure out what f and g are, and figure out what the other integral is as the result of the product rule, and then do this indirectly. So, if we don't have any knowledge right now, so we can just kind of take a stab at it. So let's say f is the 4x. Let's just go in order. And then the g prime is cosine x. So we're going to need f prime, and we're going to need g. F prime is? G is, so this is like a mini antiderivative problem, right? This is going to be sine x. Okay, so now we're going to set up our product rule here. Can I have your attention up here, please? Thanks. So we're going to fg equals integral f prime g, what did I say? G prime f. Plus and so what are we saying? We're saying this is? So we're going to say this is, we're going to just call this A for our answer, right? That's what we're going for. And then we're going to look at, so A stands for answer. And so then what is FG prime? No, I got this wrong. Sorry. That's what I wanted. Oh, I just wrote it twice. It was right. This is wrong. I need GF prime here. Okay, that's better. All right, so now what's GF prime? Well, that's our sine x times 4. And so the test to see if we picked right? Like if we picked the 4x correctly to be f or g prime, we have two ways to choose this, is this doable, right? So is the other integral from the product rule, is that a doable antiderivative? Very, right? That's pretty simple. Okay, so then over here we're going to have f times g, which is 4x times sine x. So it's like the original function that was taken the product rule of is the 4x sine x. One of the terms in the product rule was 4x cosine x. The other term was 4 sine x. That one we can do, whereas this one wasn't immediately apparent what it was. So now we can just solve indirectly. 4x sine x minus 4 4 sine x dx. Okay, and so then we say, what is antiderivative of 4 sine x? What's the antiderivative of 4 sine x? What function gives us the derivative of sine x? Negative cosine, right? So it would be negative 4 cosine x. And then this is all possible net accumulation functions. So we have the plus c. And then yes, we can do plus plus. So this ends up being 4x sine x plus 4 cosine x. Did I do all the math right? Any questions? Did you follow? Yes, sir?
How do we know that we chose the correct f?
Because this was doable. The other integral, if that one is something easy or easier, that indicates that we chose correctly. Right? So if we got 4 sine x, then yes, we can do that very simply, and then we got it. Any other questions? Yes, ma'am? What was that? Oh, yeah. Sure.
Can you explain what you did in the gradient?
Yes, so I'm trying to figure out. So remember that. So this is like the product rule, right? So my integral is of this form. So there's two factors here, 4x and cosine x. So first of all, I got to make a choice. Which one's the f? Which one's the g prime? But I'm going to use this technique. That means I need f, g, and f prime to write the other stuff. So if f is 4x, then its derivative is 4. If g prime is cosine x, then its antiderivative is sine x. And so now I'm going to use, so f times g is 4x times sine x over here. And the other integral is going to be f prime g, 4 times sine x. Does it help?
Yeah.
Okay.
Is this not integration by parts?
Yes, it is.
Oh.
Other questions? Nice and loud. The resulting, the other integral, right? So this is the one we're solving. And then you take us, and we'll gain some knowledge here. So as we do these, we'll gain some knowledge on how to pick correctly. But on the first one, I just took a stab at it. And then the resulting integral that I actually have to do the antiderivative of was doable. It was easy. So that kind of gave me it was indicated that I chose correctly. Did I answer your question? Okay. Other questions? Yeah.
Could you choose to solve for the integral of g f prime instead? Because like the answer that we're looking for is the integral of f g prime.
Yeah.
Could we?
Well, that's just like switching all the symbols. So then my f becomes g, and my f prime becomes f prime. So it's the same thing, but you're just swapping g and f.
Okay.
Yeah. Yeah.
So will most questions ask solve for f g prime, or is this?
No, you'll just get one of these. So by the time we get to the exam, we'll have like 5 or 6 techniques under our belt, and you're just going to be given accumulation functions, and you have to determine which technique to use. So the question will be, find the closed form for this family of net accumulation functions.
That would be f g in the next step, or do we just check?
What's that?
I said so. The answer would be f g because that's the antiderivative.
No, the answer. So now this integral becomes this one term of the product rule. So the answer is this minus this, and that's what I got there. Other questions? Okay. Next one. Okay, so we're always going to ask the question. We're going to start with, what small change could we make to this so that it's undoing the chain rule? What small change could we make to this so it's undoing the chain rule, first of all? Well, I should have asked the question, is it undoing the chain rule first? And so obviously it's not. So what small change could we make? So again, I want everyone to think about it, see if we can get some higher success this time. What small change, and remember undoing the chain rule is of this form. You're getting lots of practice in homework. Here's the key. The interior of the composite function has its derivative, or a constant multiple of its derivative as the other factor, right? So whatever's in the interior of your composite function, the other factor is a constant multiple of its derivative. That's what meets the requirement for undoing the chain rule. Cooper, Holland. Is Cooper here? What do you think? No progress. Okay, so do you see a composite function there? So is there one that's kind of like a composite function? X squared, is that like one function plugged into another, or is e to the 3x? Yeah, so what do we need? What's the interior function of this? 3x. So we need x squared to be something of the derivative of the interior function. So can you say what that would be? How do we change that interior function so that x squared is its derivative? What's that?
You said you need x squared to be
No, so here's our composite function. So think about the chain rule. So like I've got this function, and I do the derivative, and I get what? E to the something times x squared. What would that have to be for this to be chain rule? X to the third power, right? Third power. So if this isn't coming quickly, then you got to go back and do chain rule problems. We got to go and do so many chain rule problems that it starts to become like seeing it backwards starts to become a little more easy. Yeah.
you also just need x squared just like a constant.
Right. So yeah. Yes. And that would still be undoing the chain rule because that coefficient 3. Yeah, that's true. So yeah. So e to the 3x would be considered undoing the chain rule as well. Yeah, that's another option. Okay. Questions on that? Yeah, so if yeah, so a great help in this is just practice the chain rule and keep staring at your answer. Like look at your answer, be like, how did it relate to that first question? Because we gotta then think backwards. Okay, we don't want the 3 anymore. All right, so now we've got to figure out or take a guess. F. Oh, it's black here. Getting green. F. G. Prime. So what do we think? Notice what happens when you take the derivative. What happens to the power of x? Smaller, right? So maybe for that reason we should choose x squared here, because taking the derivative makes it simpler, right? Derivative is? So that's just a kind of a conjecture, and let's go with it. And then g prime is e to the 3x. So now I have a little antiderivative to do here. What's the antiderivative of e to the 3x? 1/3 e to the 3x. Okay, so we'll set it up now. We're going to say our answer plus integral of f g prime. Sorry, g f prime. G f prime. So that'd be the 1/3 e to the 3x times 2x. And that equals f times g. So that'd be 1/3 x squared e to the 3x. Okay, so we look at this. Is this doable? Is it easier? Well, kinda, right? So the x squared became x to the first. Maybe, is it undoing the chain rule now? Is this undoing the chain rule? He says no. Agree with that? What would this need to be undoing the chain rule now? E to the 3x squared, right? We need x squared because this is power 1, right? This would then be like the derivative of that. So it's not undoing the chain rule. Okay, so some people are picking up on it. So yes, it got easier, but it's not like straightforward and doable. If we were to put the x squared at the g prime, then our g would be x cubed, and that would be worse, right? That would be a higher power of x. So some of you picked up on it. How can we do this? We do it again. So we're going to isolate in order to solve that, we're going to isolate this, and we're going to do it again over here. So when we do that one, so I'll use capitals now. So I'm going to have, I'll do capital F and capital G prime so we don't get confused. And then F prime and G. What are we going to choose for F? Right, so if the pattern is going to hold, then if we keep picking this like monomial term, every time we take the derivative of it, the power goes down and we get something a little bit easier, right? So F can be? Sure, 2x. F prime? 2. And then G prime would be the rest. Antiderivative? If you see an arithmetic mistake or an error, please speak up, because I don't want to get to the end of this and have dug myself a hole. I do make mistakes, so don't hesitate if you think I made an arithmetic mistake. Is it looking good so far? Okay, cool. All right, so now we've got this problem, so it's going to be what? F, G. So it's like we're undoing the product rule within the larger scope of undoing the product rule, right? We got this like problem that's within it. So FG is going to be integral of FG prime plus integral of GF prime. So now I'm solving for this one, right? Call it A star for a different, my sub answer, right? My interior answer. All right, so that's plus integral, so what's G? 1/9 e to the 3x. Let me, actually, what I intended to do, you finish this one, okay? You finish the interior, the green one, right? So you can finish that problem now. Okay, off to a good start. And what about the F times G? Did you get that? Doing good so far? Okay, so now, can we actually do this one now, or do we have to do it again? Can we actually do this? So what is this equal to? This, our second kind of supposedly easier integral. Let's see, where's Anna? Hurwidge. Is Anna here? Eduardo Hopkins, where's Eduardo? Not here? Okay. Eli Nunez.
Here.
Right here?
Yeah.
Tell me, did you get that? Can you do this antiderivative? So what do we got? E to the 3x. Antiderivative of e to the 3x. So we can start with 2/9. Just pull the 2/9 out. How about antiderivative of e to the 3x? E to the 3x. Anything else? 1/3. Good. So we have the 2/9, and then we'll need another 1/3 e to the 3x for that integral. So now we're ready to write a star. What's a star going to be? Yes, sir.
2x times 1/9 e to the 3x minus 2/27 e to the 3x.
Yep, so a star will be our capital FG minus that antiderivative we just did. So 2/9 x e to the 3x minus 2/27 e to the 3x. How does all the algebra and arithmetic look so far? Anyone catching a mistake? I got lots of thumbs up. Okay, good. So that, what? So that is the value of this subproblem, right? The subproblem, and now we're ready to write out what A is. The answer to our original problem. Answer to our original problem, A is going to equal 1/3, so it's going to be this minus the answer to the subproblem, or the green problem. 1/3 x squared minus 3x minus, now we're going to need big parentheses right here because we're going to subtract this whole thing. 2/9 x to the, or x e to 3x minus 2/27 e to 3x. Okay, before I simplify that, do you follow? So we can do a little, we're going to distribute the minus, but we're essentially done. We'll also need the plus c here at the very end. Question?
Since we already defined a star of x as the thing, could we just write minus a star of x or a star since it's already like defined?
Yeah, I mean, sure, but let's
Write the whole thing.
rather than have someone have to move their eyes around the page, let's just write the whole thing. But yeah, sure. That's good because that's like the idea of function notation.
Okay.
So yeah.
I get it.
Other questions? Yeah, Tom.
Sorry, is there a reason why we don't have these integral of that now?
Of what?
The 2/9 x e to the 3x.
That was the integral of this.
Okay, that's what we were doing.
Yeah. So that's the answer to this whole thing was to figure out what this closed form was. And so now I'm substituting the closed form for the open form. Other questions? So let's write it out. 1/3 x squared e to the 3x minus 2/9 x e to the 3x plus 2/27 e to the 3x plus c. Final answer. So, how could we check that? Yes. And that would be long and ugly, right? So we'd have to do what? Product rule on that. We'd have to do product rule on that. And we'd have a fifth term, so there'd be 5 terms that we'd have to combine like terms. So we'd expect lots of things to go away. And in the end, we should get exactly that. But I want to check it a different way. Yeah.
Wouldn't you also factor up the e to the 3x and then have those 2 parts?
Oh yeah, that'd make it easier. Yeah, that's good. Factor out e to the 3x out of all these, and then you just have a polynomial left. And that'd be one product rule, a lot easier. Yep. That'd be good. Yep.
Could you make like a defined integral on top and then plug that in and then plug those numbers at the bottom to get the same answer?
Okay, so yep. Could do that. Anything else we could do? Yes, sir. Yeah. So how would I check it on GC? What would I do?
Well,
How would I check this on GC? Yes, sir.
Like you would make you plot the open form one and then you plot what you think that closed form was one is on the graph and you see if the lines are the same.
That's right. So we can graph. Let's graph the open form version and the closed form version, and then what should we see? It should be the exact same function, right? Because they're just different forms of the same net accumulation function. So I'll call the first one P and the second one Q. Rather than using F and G, which we've done throughout the solution, I'll just pick something new. Okay, so we're going to go what? ADX. Wow. I keep forgetting. Okay, from A to X of? X squared. E to the? Is that right? Yes, need T's, like always. This is what we were originally given, right? So with nothing on the integral, x squared e to the 3x, that's the same as this for all values of a. All values of a. Okay? And then also, what next? Equals?
1/3.
Okay? All right. What about the A? What about the A? So how I need to, what will I do? Plus A? Plus A? Is that right? Right. So what was it? So our closed form is use the fundamental theorem, right? So the closed form is going to be of this form, right? Equals some function evaluated at x minus the antiderivative. So the antiderivative evaluated at x, what? Minus antiderivative evaluated at a, or net change, right? The overall change from a to x. So what I'm going to do, take that, copy, say minus, parentheses, and then these have a's in them. Okay, so which one do I trust? Which one do I trust, P or Q? You trust P. We know that's right. We know that's going to be the right net accumulation function, or family of. Okay, we're checking Q. We're trying to see if all this math we did is right. So we're checking Q. And we trust P. So how are we going to do that? So let's graph P first. And we need to choose an A. I heard 1 and 0. I had more zeros. Just use 0, right? Can I erase all the writing? Like, please, quick. Okay? Graph. So here's the function, and the moment you've been waiting for, graph the other one, starting at 0. And we should see exactly the same. So that's without the new one that the closed form. This is with both. What if, okay, so they are the same net accumulation function. What if I were to start one at a different value of A? What will we see? Shift. Shifted left, shifted right. So remember what this is. This is all functions, net accumulation functions of a quantity, what? Whose rate is that. So what would all accumulation functions that have that rate, how would they be related? Are they left-right shifts with one another? What is it? Yeah, it's gonna shift. Too much. Why does it shift? Is this right? Why is this right? Talk about it. Talk to somebody. Why is this right? Explain.
When you subtract the agents, so that's what that is. So f of 0 is probably 0.
Yeah.
X minus f of a. And so that the reason why it goes downward is because it's subtracting that f of a and that f of a. The plus c is infinite variables of f of a. Subtraction.
Okay, who thinks they have some insight here? Samuel? Yes, ma'am. We forgot to do something? You're saying the functions are defined?
No, I'm just saying that I would know how to do the GC, but because our angle on paper has a plus C, which is the
Okay. Does this have the plus C? What's the plus C on this one?
0.
No? That's the plus C right there. Right? So that's the plus C. So, other thoughts? Somebody new? Tom?
Because the C in this case is like our y-intercept, and because it's negative in this case, when we increase our a value, it decreases our y-intercept, so we go lower.
Okay. So a matter of y-intercept, so it moves it up or down. Other insights here? Yeah, same.
There's less net accumulation. That's why it's lower.
Yeah, so where does the net accumulation start for this one? Notice that it's 0 at 0, right? And where does the net accumulation start for this one?
1.
So we need to maintain the rate, it's the same rate function, but have it so that at 1 it's 0, right? The net accumulation is 0 at x equals 1. So how do we maintain the same rate of change?
Subtract the value, add to 1 for the p of 0, x.
Right, because this is for our example, this is what, minus f of 1. So maintaining the rate means moving it up and down, right? Do you see those two functions have the exact same rate function? For any value of x, there's the same rate of change. But then this one starts accumulating at 1, this one starts accumulating at 0. That's why changing the starting point of accumulation will move it up and down, not left and right. Okay. Any questions? Okay, so this is a great means of checking all that algebraic work you did. So you can, put in the one you trust, put in the open form, graph that, and then put in closed form and graph that. And they should be right on top of each other. If you graph it with the same starting A value, they should land on top of each other. Okay, next one. Integral ln x dx. Here we go. So the first question we ask is it undoing the chain rule? Is it undoing the chain rule? No. Okay? So we won't ask how to change it. We'll just move on. So this, when you have natural log, oftentimes natural log deal with undoing the product rule. So we got our f prime and our g. So, but we only got one thing. So what do we do?
1 dx.
So one of these two is going to be natural log of x. So is it going to be f or g prime? Now look what happens if you make it g prime. Then what do you have to do? You have to do the antiderivative ln of x. That's the problem we're given. This isn't going to work, right? So you only have really one choice. Is to make it f. Derivative is? Okay. So then what would g prime be? Right, 1. Right, 1 times ln of x gives you ln of x. Then g is? X. Here we go. So we're going to have a plus integral 1 over x times x equals f times g. What's that?
X.
That's just 1 antiderivative
X.
x. So we're going to have a is going to be x ln of x minus x plus c. So remember we saw that x squared e to the 3x? How many iterations of undoing the product rule did that take? 2. And we saw 4x cosine of x. How many did that take? So where's that number coming from, right? Right? So how many times will this take?
Approximately 9.
No, do it. These are different. So, on your own time. But do it and find out that it's not 9, doesn't take 9 times. Doesn't take 9 times.